In this module, we're going to start focusing a little more on the stoichiometry, but if we have a limiting reactant, meaning something is limiting how much I can produce of an overall product. We're also going to talk about some with that theoretical yield, and then our percent yield of the reaction, basically how efficient is a reaction. So first, we got to cover some terminology. Reactants, reaction stoichiometry, and limiting reactants specifically. So again, what if we're given amounts for both reactants in a reaction? So far, when practicing stoichiometry, we've just said this much reacts or this much is produced. But what if I'm told I have two pieces reacting? I have this much for each species. How do I decide how much product I can actually make? For example, take it out of the world of chemistry. You're at home, you're folding your socks, and if you don't have all the socks come out of the dryer, how are you matching them up? You're going to have an excess of one over the other, right? It's the same kind of thing here. What if I have an excess of one chemical over another? When I look at the picture up here, I've got H2 reacting with O2 to form H2O. And I see it says plus O2. Why does it say plus O2? Why am I not just forming water? Well, I've got 4 molecules of H2 here, 3 molecules of O2, but the balanced equation is H2O, meaning that for every 2 of my hydrogens, I only need half of my oxygen. 2 more hydrogens, the other half of my oxygen. 2 more hydrogens, half of my oxygen. 2 more hydrogens, the other half of my oxygen, which leaves me with an excess of 1 oxygen molecule at the end of the reaction. So I can't just look at the balanced equation directly. The balanced equation is needed, yes, but I have to do some math on it and figure out how is the balanced equation, along with the mass of those species, directly telling me what is my limiting reactant, what is my excess reactant. So one of the reactants will be completely consumed or reacted in a reaction. The other reactant will be present in excess, meaning some reactant is left over at the end of the reaction. The reactant that limits the amount of product that can be made is known as your limiting reactant. So limiting reactant is completely consumed, and also limits the amount of product that can be made or produced. So common questions I want you to ask. Which chemical is my limiting reactant? How much excess reactant remains after completion of the reaction? And how much product can be formed? You have to use your limiting reactant to answer this question. Basically, conservation of mass. I cannot produce more than I have available. Like if I run out of reactant, no more can be produced. So my amount produced is absolutely limited on my limiting reactant. So some overall definitions. I know we talked briefly about a couple of these in the previous slide, but just give you all the definitions in one. Limiting reactant, also known as your limiting reagent. Reactant and reagent, those terms are interchangeable. It's the reactant that's completely consumed or used up in a chemical reaction, and it limits the amount of product produced. Your reactant in excess is any reactant that is in a quantity greater than required to completely react with the limiting reactant. This will be left over, some of it, at the end of the reaction. Your theoretical yield is the amount of product that can be made in a chemical reaction based on your limiting reactant. Basically what that means is if everything goes perfectly, there's not any issues, there's no side reactions, there's no loss of product, how much could I make? Theoretically, how much can I actually produce? The actual yield is the amount of product produced by a chemical reaction. The theoretical yield and actual yield may match, but most of the time will not because reactions are not perfect. Percent yield is a measure of how well this reaction went, the efficiency of the reaction. How much product did you obtain from the reaction in percent form? We take your actual yield, divide it by your theoretical yield, and multiply it by 100%. And your atom economy is a concept under green chemistry. We won't delve into it much in this class, but I like to introduce it because I think you guys should start thinking about it. And it's basically how many atoms in the reactants become atoms in the products. It's the molecular weight of your desired product or the molecular weight of your all reactants combined times 100. It looks at, I put this many things in, all I wanted out was this, how wasteful was my reaction? So let's talk about your limiting reactant. Let's look at a Chick-fil-A sandwich, okay? So a Chick-fil-A sandwich includes 2 pieces of bread, the top and the bottom of the bun, 1 piece of chicken, and 2 pickle slices. If I had 8 pieces of bread, 5 pieces of chicken, and 10 pickle slices, how many sandwiches could I make? Most students are going to look at this and they're going to very quickly say, okay, you can make 4 sandwiches. Why? Because it's limited by my bread. I have excess pickles and excess chicken. Specifically, I have 1 excess chicken and 2 excess pickles. But what if I was to do this by stoichiometry? I would say, how many sandwiches can I make with each species? If I have 8 pieces of bread, I know that each sandwich takes up 2 pieces of bread. That's giving me 4 sandwiches. If I look at my sandwiches based on my chicken, I have 5 pieces of chicken. 1 sandwich takes 1 piece of chicken. I could make 5 sandwiches. If I look at my pickles, I know I have 10 pickles. I know 1 sandwich requires 2 pickles. Overall, I could make 5 sandwiches. I say I'm still limited to 4. I know that 4 sandwiches is the max I can make if I have 8 pieces of bread, 5 pieces of chicken, and 10 pickle slices. In this case, the bread runs out first. Therefore, my bread is my limiting reactant. My excess reactants are anything that is left over once complete. I have an excess chicken, and I have 2 excess pickles. The other way I could figure out my excess, I know I can make 4 sandwiches. This told me 5. 5 minus 4 is 1 extra sandwich. Same here. These could make 1 extra sandwich than what I'm limited to. But how do I figure out my excess remaining? Mathematically, I would say, well, 1 sandwich requires 1 chicken, so I have 1 chicken remaining. 1 sandwich requires 2 pickles, so I have 2 pickles remaining. Most of us, again, can do this in our head pretty quickly. Once we get into chemicals, it becomes a lot more difficult. So let's go ahead through the process. This is the process I want you guys to try to start following. If you do it this way, if you've learned another way in high school, that's fine, do it. But this way is what students, when students do it this pathway, they tend to get all of the questions like limiting reactant, theoretical yield, excess reactant correct more often than not. So try to get yourself following this pattern. Step 1, convert what you're given to moles. Step 2, ask yourself a question. If I use up all of one of the reactants, how much of the other one do I need? Step 3, answer this question using mole ratios. Step 4, ask the question, do I have it? Do I have enough? Assign labels of limiting and an excess. One of your reactants will be limiting, the other reactant or reactants will be an excess. Use the limiting reactant to solve the original stoich problem. So let's go ahead and do that. We've got here, in a commercial process, nitric oxide, NO, is produced. What mass in grams of NO can be made from the reaction of 30 grams of NH3 and 40 grams of O2? Now, NH3, again, that is the common name for that is ammonia. We should start practicing naming. Naming does, we have covered naming at this point. We do need to practice naming. And again, nitric oxide is the common name for this. You could also say nitrogen dioxide would be fine as well. I like writing on these exactly how much I have of each thing. I'm going to have to write this above though, because we're going to need space on this side. So I know 30 grams of this and 40 grams here. First thing I want to do is convert what I'm given to moles. So I'm going to go ahead and bring this in because we're going to need a lot of space in this slide. Number of moles of NH3. I'm given 30 grams of NH3. I know that 1 mole of NH3 weighs 17.03 grams. Why do I know that? Because I added up the molar mass really quick. Make sure that my grams cancel with my grams. I'm left with moles, so my conversion is set up correctly. And I get 1.76 moles of NH3. And do the same thing for number of moles of O2. I have 40 grams of O2. I know that 1 mole of O2 weighs 32 grams. Why? Again, I added up the molar mass. Make sure that what I want to cancel is canceling and I'm getting the units I want. And I find that I have 1.25 moles of O2. Now the second step is ask myself, how much do I need of one reactant if I use up all of the other one? And I answer this question by using a mole to mole ratio. So I'm going to say, okay, well, how many moles? And it's random. I pick randomly. I usually pick the first one. I pick randomly. But I'm going to say, how many moles of NH3 to react all of my O2? If I want to react all 1.25 moles of O2, how many moles of NH3 do I need? Now to do this, I do need the balanced equation, and I want to draw these off. I'm trying to box things in for you guys so that we can see it going through a little bit. So this is step 1. Working on step 2. Or step 2, 3. I see that 4 moles of NH3 react with 5 moles of O2. So I know it's 4 moles NH3 for every 5 moles of O2. Make sure everything's canceling. That is canceling moles of O2 and giving me moles of NH3. And I get an answer of 1.00 moles of NH3. Now I'm going to ask myself, do I have enough? I am comparing the moles needed. This is how many moles needed to react all of my O2. And I have 1.76 moles of NH3. I ask myself, do I have enough? And the answer is yes, I do have enough. That is step 4, by the way, asking myself, do I have enough? So now that I know I have enough, I'm going to assign labels of limiting and in excess. The species that's going to run out is my limiting reactant. Oxygen is my limiting reactant. Ammonia is in excess because I have more than enough ammonia to complete the reaction and the O2 will limit. So we can see limiting is O2. That is supposed to be an arrow right there. And NH3 is in excess. So again, just your limiting reactant. O2 runs out first. It is completely reacted. Your excess reactant is ammonia, and we have more than we need. We only need 1 mole of it, and we have 1.76 moles. So step 6, solve the original stoich problem. I'm going to use limiting reactant to solve this because it's going to run out first. I'm going to use my limiting reactant. So I want to know number of grams of NO produced if I start with 1.25 moles of O2, 4 moles of NO are produced for every 5 moles of O2 consumed. That gets rid of my moles of O2. Now I'm to moles of NO, but I don't want moles, I want grams. I add up the molar mass of NO, find to be 30.01 grams. NO to 1 mole of NO. That's canceled out my moles of NO, and I've now gotten to grams. And I calculate this out, and I get a final answer, 30.0 grams of NO. Be careful here, 3 sig figs, 3 sig figs. If I plug this in my calculator, I'm going to get 30.01. I don't want to leave it like that because this is my sig figs. This is exact, so it does not limit sig figs. It is exactly 4 moles of NO that react with exactly 5 moles of O2. This is to 4 sig figs, so it's not going to limit it, but I am limited to overall 3 sig figs. So, measuring the success of a reaction. The amount of product collected at the end of the reaction, or my actual yield, is often less than the yield than we predict we should be getting using your stoichiometry. And so in order to, and we'll talk about why in a sec, but in order to measure the efficiency of a reaction, we can use percent yield, most common in our class, or atom economy. Again, atom economy, you're not going to see as much, but it is a green chemistry concept. So how can we be more sustainable and more conscientious of the environment and the world we live in without being wasteful? As an example of atom economy, look at these M&Ms. Now, I don't actually know how many M&Ms are there. Let's say we have 22 M&Ms total. I don't actually feel like counting them. Let's say we have 22 total, but all I want is the green M&Ms. Green M&Ms are my favorite. I don't know why. They just are. We've got 3 green, 22 total, times 100%. Molecular weight of the desired product, molecular weight of all the reactants. Now we're just saying that the molecular weight is 1 for each M&M, but 3 divided by 22 times 100. This gives me 13.6%. It's not very efficient on the reaction, right? I'm making all these M&Ms, but I'm only going to take the green ones out. Well, that's not a very efficient way to do it. I should find a better pathway. That's what atom economy is looking at. Percent yield, on the other hand, doesn't much care about what went into it. It more cares about what am I getting out of it comparative to what I should get out. So your actual or experimental yield divided by your theoretical yield times 100%. That theoretical yield is what we just calculated using stoichiometry. It's your limiting reactant and it's your stoichiometry. So why is the, I apologize, it's supposed to have more things in this slide. It didn't copy over correctly into the PDF. But why is the percent yield of reaction never 100%? Well, number one, reactions do not always go to completion. Why? Because you can have equilibriums. We're going to study that a lot more in second semester Gen Chem, but an equilibrium's reaction can go forward and backward. And so we find kind of a happy in-between between the two. You could have impure reactants. When I buy reagents from a chemical supply company, most times I'm buying things that are 97 to 98% pure, but that's not 100% pure. And I'm not going to pay for 100% purity when it's just not worth the cost to purify to that point for what I need for my students to do in a class. So you can have impure reactants, you could have side reactions. That may cause other products to form. Some of the product could be lost through things like filtration, being left behind in a beaker, etc. Maybe it's a liquid and it's evaporating. And so you're not going to get 100%, excuse me, 100% yield because you're just losing your product other places. I apologize. So for our last example for this module, let's go ahead and work this example. In this reaction, magnesium solid reacts with I2 solid to form MgI2 solid. If 10 grams of magnesium reacts with 60 grams of I2 and 57.84 grams of MgI2 form, what is the percent yield? Well, let's go ahead and figure it out. First thing I want to do is figure out the moles of each species. So number of moles, magnesium, 10.0 grams magnesium. 1 mole of magnesium, I look at the table and I see it's 24.31 grams. And notice I'm labeling what I'm doing here. The moles of magnesium, the grams of magnesium, I'm labeling magnesium on everything so I'm not mixing up what I have. Don't just put down random numbers because you're going to lose track of what those numbers represent. What I mean by that is don't just write down 0.411 moles and be done with it. Write down 0.411 moles of magnesium so you're very clear that it's magnesium that you've calculated. Number of moles of I2, 60.0 grams of I2. 1 mole of I2 is 253.8 grams of I2. Again, it is 2 iodine, so I have to take the mass off the table, which is like 126.9, I think. I'm doing this by memory, I apologize. And multiply that by 2 to get the mass. Calculate this out, and I get a value of 0.236 moles of I2. Now I'm going to ask myself, if I react to all of one, how much of the other one do I need? So I'm going to say, how many moles of magnesium do I need to react all of my I2? I've got 0.236 moles of I2. I see it's a 1-to-1 ratio, which is convenient. 1 mole of magnesium to 1 mole of I2. Some students may say, why do I have to do this step? Because I can see clearly from the reaction that it's 1-to-1, therefore I2 is my limiting reactant. I don't care. If you want credit for the question, you show the work, okay? Because it's not always going to be 1-to-1. So you do have to show that it is 1-to-1. 0.236 moles of magnesium needed. Do I have enough magnesium? Yes, I do. Why am I happy? So I have to do the calculation the other direction. I already know. I'm going to go ahead and label these. This is going to be my access reactant, and this is my limiting reactant. I'm now going to use my limiting reactant to determine my theoretical yield. So number of grams, MgI2, if I react 0.236 moles of I2, 1 mole of MgI2 reacts with 1 mole of I2. I'll move this because I'm going to run out of room. Add up the molar mass of magnesium iodide, and I get 278.1 grams of MgI2 for for every 1 mole of MgI2. And I see that the answer here is 65.6 grams of MgI2. Well, what does that mean? That means theoretically, no problems, no mistakes, no nothing, I would obtain 65.6 grams of MgI2. I didn't. I have to calculate my percent yield. I obtained 57.84 grams. So that's my actual yield. Where is this? My theoretical yield. Divide that by 65.6 grams times 100% gives me an answer of 88.1%. Now, this had 3 sig figs, so my answer here had 3 sig figs. 3 sig figs here, 3 sig figs here. 3 sig figs here, 3 sig figs here. This had 4 sig figs, but this only had 3 sig figs, which means my final answer can still only have 3 sig figs. In the next video, we will work more complex examples, but I wanted you guys to get a basis.